Consider the language L given by the regular expression a plus b star b a plus b over the alphabet a comma b. The smallest number of states needed in deterministic finite state automata DFA accepting L is. This is a question from finite automata section from theory of computation. So we have been given this language. We need to find out the minimal DFA accepting this language, and we need to write the number of states in the minimal DFA. Now the minimal DFA for a regular language will be unique. So this answer will be a unique one. So we can try to solve this now. Now first I will draw the NFA for this language. It's given that the language is a plus b star. It starts with a plus b star. So that I will given as this. Initially for each a and b we remain the same state, and then on seeing b we go to a next state, and then a or b we go to the accepting state. So this is the NFA for this language. Now what this language does is this language accepts all strings ending with BA or BB. So this is the language, all strings ending with BA or BB, and this is the NFA for this language. We need to find the minimal DFA for this. Now there is a procedure for converting NFA to its corresponding minimal DFA. Now the procedure is given clearly in the video lectures, finite automata section of theory of computation section. So you can refer to that video lectures to find out how the procedure works. But for this question I won't be using that procedure. I will be just looking at the language and I'll try to construct a DFA directly from here and find out the minimum states. So if you look here, for this state, for B I am coming to this state as well as I am going to the second state. So this we need to eliminate, this part of NFA. For the same B we are going to two states, and also for these two, for this state A and B it's going here. For this state for A and B I haven't given any output. That also I need to provide to convert to DFA. So let us start from here. Now as long as we see A's, it doesn't matter because it's a string ending with B or A. Only when we see the first B it matters. So let us say that for A we go to the same state, and on seeing the first B I go to this state. Now it's all string ending with B A or B B, right? So on seeing the next A or B I can go to this state. Okay, so this seems correct. Now from this state I need to write transitions for input symbols A and B. So let us see that. So if the next state is B, there are two ways of reaching this state. One is BA, we saw B or A and now we are looking at B, or the next is B or B, we saw and reached this state and now we are looking at B. Now if this is the state, if this is the case, we'll see that the last two terminals are BB, which is again the accepting state. So on B I will go to the same state only, the same accepting state. But if this was the case, if we saw a B and then we saw an A and came to the state, we'll see that on seeing the next B it is AB. So that doesn't correspond to the accepting part, it's ending in AB, so that clearly we can't accept this. So the state which we can go to is, we can go to this state. We saw one B, so that on seeing the next A or B I can accept. So on B itself I need to go to either this state or this state depending on what I saw on arriving to this state. So that what I saw on arriving to this state, that I need to save. I can't just write it in one state. So we will split these states again. Let us say on A I came to this state, and on seeing B I'm coming to this state. Now we can try to draw transition symbols here. For this state we have arrived at this state using BA. Now on seeing A, the ending part will be AA. Using AA we can't take it to this state. For this state we have to have seen a B previously. So meaning that on A I need to go to this state only. It is AA, so I'll go to this state. Only after seeing one B and one A or B only I can go to any of the accepting state. This is the transition for A from this state. Now the transition for B is that if we have B, A, B, I can still go to this state, right? I can go to this state on B. On seeing the next A or B, I can go to an accepting state. So this is the transition for B. For this state, if it's B, we reach this state from B, B. If we see one more B again, it's again B, B, ending in an accepting configuration. So on B, I can go to the same accepting state. On seeing A, similarly, I need to go to on seeing A, what happens is we have seen B, B already, and now it is BA, which is again an accepting state. So on BA, it's an accepting state, but it won't be going back to this same state. When we are accepting with BA, it was this state. So on seeing A, I need to go to this state. This state means we have already seen BA so far. So this is the minimal DFA given in the question. You can verify this state I have given transitions for A and B, this state I have given transitions for A and B, this state I have given transitions for B, A, this state also I have given transitions for A and B. So this is the minimal DFA for the language given here. The number of states is 4.